Let us now look at nucleon number, proton number, and nuclides. Nucleon number is simply denoted with A, and this is the number of the sum of protons and neutrons. Better still, I can simply just say this is just the sum of protons and neutrons. So nucleon number A, symbol A, is the sum of protons and neutrons. While proton number, denoted with letter Z, is just the number of protons. Then what is a nuclide? A nuclide is represented with X, proton number on the top left hand side. Nucleon number on the top left hand side, proton number on the bottom left hand side. Is a species that has a definite nucleon number and a definite proton number. So any species with a definite nucleon number and a definite proton number is a nuclide. E.g. alpha 42, which is also called the helium nuclide, helium 42. Okay? Beta 0-1, neutron 10, proton 11, carbon 12-6. Any species with a definite nucleon number and a definite proton number is definitely referred to as a nuclide. Then what are isotopes? Isotopes are nuclides with same proton number but different nucleon number. E.g. hydrogen 11, hydrogen 21, hydrogen 31. All these are isotopes. So remember that I did not limit this by saying that isotopes are atoms, because you don't need to be alike atoms to exhibit isotopy. These are nucleons of hydrogen, and they are what? Isotopes. Provided it has a definite nucleon number and a definite proton number, it is a nuclide. So when you have nuclides with the same proton number but different nucleon number, then that nuclide is an isotope. Example also is the oxygen 16-8 nucleus and oxygen 18-8 nucleus. All these are isotopes. All right. Now let's look at nuclear reaction. A nuclear reaction consists of a parent nuclei bombarded with a projected particle to then produce daughter nuclei with the release of ejected particle. Then energy. Example, parent nuclei XAZ bombarding a projected particle. Let me call it A, letter A prime, Z prime, to give daughter nuclei, which is Y A double prime, Z double prime, plus ejected particle, B, A triple prime, Z triple prime, plus what? Energy. Why did I write each of them to have their own nucleon number and their proton number, using the prime to differentiate them? Is to show you that all of these are actually nuclides. Nucleus, particle, and so on and so forth. And it can be nucleus. But what we are explaining to you that a nucleus is a nuclide, particles are also what? Nuclide, provided they have definite nucleon number and definite proton number. Now let's look at conservation laws in nuclear reaction. Conservation laws in nuclear reactions. Number one is conservation of nucleon number. In a nuclear reaction, nucleon number must be conserved, i.e., sum of nucleon numbers of the species on the left-hand side must be balanced by the sum of nucleon numbers of the species on the what? On the right. Okay? So when you are balancing a nucleon number, when you add up the nucleon numbers of the species on the left, it must be equal to the sum of the nucleon numbers of the species on the right. Number two, conservation of proton number. The same way, sum of proton numbers of the species on the left must be balanced by the sum of the proton numbers of the species on the right. So when you add the sum of proton numbers of species on the left, it must be balanced by the sum of proton numbers of the species on the right. Number three, conservation of sum of mass and energy, i.e., or basically conservation of energy. And I will explain that. So, in a nuclear reaction, mass is not conserved, i.e., the mass of the species on the left will not be the same as the mass of the species on the right. The difference in mass is converted into what? Energy. The difference in mass is converted into what? Energy. So what is conserved in a nuclear reaction is actually what? The sum of mass and what? Energy. So what that means is that if you add the mass, if you add the energy values of the mass and energy on the left hand side to the energy values of the mass and the energy on the right hand side, then that is when the equation is what is balanced. That is why we are saying that what is actually balanced is the conservation of what? Energy. Because every mass has their energy value. So energy value of the mass on the left hand side will be balanced by the energy value and energy on the what? Right hand side. Therefore, we can say that in a nuclear reaction, it is the energy on the left hand side that is balanced by the energy on the what? Right hand side. So let me elaborate on that. Number three. In a nuclear reaction, mass is not conserved, i.e., sum of mass on the left hand side is not equal to sum of mass on right hand side. The difference in mass, which is known as mass defect, is converted into energy. Okay, i.e., energy on the left is balanced by energy on the right. So it is when you add the mass and the energy on the left hand side that will be balanced by the mass and energy on the right hand side. So we are saying that all this mass has an energy value. So if the mass on the left-hand side is greater than the mass on the right-hand side, the difference in mass that is converted into energy will be added to the right-hand side. But if the mass on the left-hand side is less than the mass on the right-hand side, it means that energy on the left-hand side is less than the energy on the what? Right-hand side. The difference in mass that is converted to energy will be subtracted from the right-hand side, so that you are going to have a balance of energy on the left-hand side and also on the what? Right-hand side. Let's look at some illustrations. Let's look at some illustrations. Let's look at some illustrations. For example, let us say aluminium 2713 bombarded with alpha 42. This will give phosphorus 3015. The ejected particle will be 37 plus 4 is 31. Then you have 30 plus 1. Then 13 plus 2, 15. 15 plus 0. So that means the ejected particle there is a neutron. Okay? The ejected particle there is a neutron. So when you are balancing a neutron number, the sum of neutron numbers on the left-hand side will be balanced by sum of neutron number on the right-hand side. Sum of proton number on the left-hand side will be balanced by sum of proton numbers on the right-hand side. Okay? So also if I have okay, so that is that. Okay. So I can also have something like hydrogen 2,1 plus hydrogen 3,1. This gives helium 4,2 plus a neutron. Okay? Okay? If I have uranium 23592 plus neutron 10, this now gives barium 14056 plus krypton, barium 14356 plus krypton 9036. So if I want to balance this, sum of nucleon number on the left is 235 plus 1, 236. 143 plus 90, 233. Then 92 plus 0, 92. 56 plus 36, 92. So that means what I'm going to be having here is a neutron, because the nucleon number of the ejected particle is 0. But I'm going to be having 3 neutrons. So as time goes on, we also, with the release of energy, as time goes on, we are also going to be talking about more of these examples. Okay? Now, quickly, let's talk about the discovery of the nucleus. How was the nucleus discovered? A very, very important day in the world of science, when the nucleus was discovered. So when we say the nucleus was discovered, it means that it was at that point in time, during the evolution of atomic physics, that we concluded that the nucleus actually existed. This means that prior scientists that have described the nucleus did not describe the nucleus to contain, prior scientists that have described the atom didn't describe the atom to include the nucleus. Example of that is J.J. Thomson. Okay? J.J. Thomson described the atom as a positive sphere with the electrons embedded in it. There was no room in that his discussion that the atom actually contains the what? The nucleus. So how and when and how was the nucleus discovered? The nucleus was discovered. The nucleus was discovered in an experiment known as alpha particle alpha particle scattering experiment. That's the name of that experiment. Alpha particle scattering experiment. So what happened in this experiment was that two scientists in the name of Giga and Marsden bombarded a gold foil with alpha particles. And they observed the following. They observed the following. Number one, most of the alpha particles were undeviated. Like this. Most of the alpha particle passed through without being deviated. Second one, some of the alpha particles were deviated at large angles. Like this. Some of the alpha particles were deviated at large angles. Are you following? Then the third one is this. Few of the alpha particles were deviated at angles greater than 90 degrees. Few of the alpha particles were deviated at angles greater than 90, which is something like this. Are you there? So most of the alpha particles were undeviated. This shows that most part of the atom is essentially an empty space. So this shows that most part of the atom is an empty space, which is a vacuum. Some of the alpha particles, which are positively charged entities, were deviated at large angles. What does that show you? Some of the alpha particles were deviated at large angles. What does that show you? Does it show attraction or repulsion? Repulsion. For the alpha particles to have been deviated, that shows that there must be a positive core inside the atom responsible for that deviation. So this one shows that there is a positively charged core inside the atom. That is what this one is showing. There's a positive charged core inside the atom, concentrated at a single position, at a single point. So you don't have several positively charged cores inside the atom. Otherwise, you will have seen sporadic what? Division. But you have only one positively charged core inside the atom. That's why you just have the alpha particles deviated at large angles. There is this third one, in which few of the alpha particles were deviated at angles greater than 90. If few of the alpha particles were deviated at angles greater than what? 90. If few of the alpha particles were deviated at angles greater than 90, it means that out of the many alpha particles bombarded to the nucleus, only few of them were coming in direct contact with that positive charge core. What does that tell you about the size of the positive charge core? It shows that the size of the positive charge core is small compared to the entire size of the what? Atom. So this showed that the size of the positively charged core is small compared to the size of the atom. That is what this third one is showing. That the size of the positively charged core is small compared to the entire size of the what? Of the atom. So the conclusion from this experiment is that the atom contains a positively charged core that is small compared to the entire space of the atom. In conclusion, the conclusion of this experiment, the atom contains a positively charged core that is small in size compared to the size of the atom. That is the conclusion. So the alpha particle led to the conclusion that the atom contains a positively charged core that is small in size compared to the size of the atom. Then Ernest Rutherford named the positively charged core the nucleus. That is why it is now referred to as the Rutherford nuclear model of the atom. So Rutherford was the supervisor of Giga and Marsden. So experiments have shown that the diameter of the nucleus is of the order of 10 to the minus 15 meters. While the diameter of the atom is of the order of 10 to the minus 10 meters. So I can see that the nucleus is like 10 raised to the power 5 times, that is hundreds of thousand times, 10 raised to the power 5 times smaller to the what? To the atom. So the nucleus is like 10 raised to the power 5 times smaller in size compared to the what? Atom. Or the atom is 10 raised to the power 5 times greater in size compared to the nucleus. Is that clear? Okay. So now let's look at radioactivity. It has been observed that certain nucleus by themselves disintegrate. What does it mean to disintegrate? To disintegrate means to break down. So those nucleus breaks down on their own. And in the process of breaking down, they emit certain particles. Those particles are said to be radioactive particles, which are alpha particles, beta particles, and gamma rays. But that disintegration is a spontaneous disintegration, and it's also what? Random disintegration. It is spontaneous because the rate of disintegration is not affected by external factors, e.g. temperature or pressure. Why it is random? Because the disintegration is based on probability. Or we can say the count rate fluctuates. So here, you can't predict the nucleus that will disintegrate next. It is based on probability. So if a disintegration is occurring spontaneously and it's also occurring randomly, then that disintegration is a radioactive disintegration. It is not all disintegration that is a radioactive disintegration. For example, calcium carbonate can disintegrate in the presence of heat into calcium oxide and carbon dioxide. It is not a radioactive disintegration because this disintegration is not spontaneous. It can only occur if I apply heat to calcium carbonate. By itself, calcium carbonate will not disintegrate into calcium oxide or carbon dioxide. But if a radioactive nucleus is disintegrating in Nigeria and it's also disintegrating in Russia and they have the same mass, after 30 years, the mass would have reduced by the same amount. If the mass you have at the beginning of that particular atom disintegrating in Nigeria, so it's the same initial mass you have in Russia, after a particular time you still have the same mass because that rate of disintegration is not affected by external factor. That is why they are basically used for radioisotope dating. Okay? So, radioactivity is the spontaneous and random disintegration of a radioactive nucleus to leading to the emission of radioactive particles. What are these radioactive particles? Alpha particles, beta particles, and gamma rays. Leading to the emission of radioactive particles. What are these particles? Let me write them out fully. Alpha particle, beta particle, gamma rays. So beta, you can be having beta minus or beta plus 1. Then gamma rays. So radioactivity is spontaneous and random disintegration of a radioactive nucleus, which leads to the emission of radioactive particles. What are these particles? Alpha particles, beta particles, and gamma rays. It is spontaneous because the rate of disintegration is not affected by external factors. It is random because the disintegration is based on probability, meaning that the count rate fluctuates. So, if I draw a decay curve, if you sketch a decay curve, the decay curve will show that the number of nuclei, they are reducing exponentially with time. The number of nuclei at time is equal to 0 is known as N0. So it's reducing exponentially with time. If you change the temperature of this system, it will not affect the rate of disintegration, which means that the gradient of the decay curve is the rate of disintegration and is not affected by changing the external factor. Unlike a rate curve, rate of chemical reaction, the gradient is affected by external factor. So if I increase temperature, this will be for increased temperature. This will be for lower temperature. This is the normal one. But a decay curve, because it is spontaneous, the gradient of the curve, that's rate of decay. Rate of decay is not affected by external